Hi everyone, my name is Predrag Nikolic. I'm a verification engineer at a company called Veriest Solutions. Today I'll present you my paper called Is Your System Security Preserved? Verification of Security IP Integration. Let's start. This presentation will start with the introduction to the security system verification. So in order to understand this methodology, I'll first need to explain the security system structure. The best way to present this methodology is through the test plan. Therefore, I'll list all the tests used in order to verify the security system integration. You'll notice that first two tests and probably the most important tests are related to boot flows. Therefore, I'll pay specific attention to explaining these flows. And then I'll continue with showing each test used, and the presentation will end with listing all the RTL bugs and drawing conclusions. Security system is present in most of today's SoCs. It's very common in automotive industry, especially is used in autonomous vehicles. The role of the security system is to detect outside attacks, such as fake data injection or sensor replacement or software modifications. It also needs to prevent access to the sensitive data such as keys and certificates. Besides that, security system needs to provide service, and two most common services are data encryption and generation of true random number. Now this paper assumes that the IP is obtained from vendor, which means that this IP is verified in block level on their end with certain guarantees that the verification is done correctly. Now, this is not enough. When this block is integrated into the SoC, also some vulnerabilities can be introduced with it. So we need to verify that the integration was done correctly. The approach used in this paper is to detect gaps between block level and system level verification and to verify only these gaps. It's important to mention that this paper uses functional verification with system Verilog UVM. At the beginning, I'll first present a security system structure in order to be able to understand the methodology which comes in the following slides. So at the first glance, this picture may look complex, but it really isn't. So you'll see that security IP contains many blocks which are very common and we all know them, but it also has some specific blocks. So it has its own CPU with its associated IRAM, DRAM, boot ROM, and OTP. It also has mailbox, which is used to get instructions and manage them from the main CPU. It also has two DMAs, which are used to transfer large amounts of data. It also has debug unit, which is very important and through which the main CPU can access the complete address space of the security unit. So regarding specific blocks, it has crypto engines which are used for data encryption. It also has TRNG, which stands for True Random Number Generator. As the name says, it generates random number. It also has digital sensors, which are basically used to detect anomalies such as changes in frequency, voltage, and temperature. In the upper half of the picture, you can see that security IP is connected to the rest of the SoC through the system interconnect unit, which is usually some network on chip, and it's connected to all the blocks that it needs to protect. So I didn't draw all blocks in this picture. I draw only two which I find most important: main CPU and memory. As I mentioned in the introduction, the best way to present this methodology is through the test plan. So on this slide you can see the list of the tests used for this. So please note that this is a minimal set of tests, so in reality you may have more tests, but these are for sure essential tests. So first two tests are related to boot flows. There are two boot flows. One is non-secure boot flow and the other is secure boot flow. These tests are probably two most important tests, and in the next slide I'll actually first explain boot flow and then each of these two tests. So next two tests are related to service requests. So first is TRNG test, which is less complex and is followed by crypto service test, which adds more complexity to these requests. Next two tests are related to debug interface, which is a very important block. So one test is related to non-secure and the other is to the secure mode of operation, and we'll see what is the difference. The tests that follow is hardware alarm and interrupt test, so we'll see why we need to check this feature as well. The last test is related to performance, which is very important because we want to make sure that we did not negatively affect the performance of our system when integrating security units. We all know is that when SoC is powered on, the first thing it does is that it executes power up sequence. Now PMU unit is mostly responsible for this. What does it mean? It takes all blocks out of reset and provides clock to them in certain order. Now when security unit is available in the SoC, then it is usually also involved in this power up sequence, because in case a security unit is corrupted or compromised, we may not want to actually enable the system. Now, how is it involved? Well, it can be involved in many cases, so this is defined by the architecture, but it usually, first thing it does is that it reports back to the PMU unit that it is awake, so security IP is awake, it's up and running. In case this information is not provided, then PMU needs to execute a certain sequence for this scenario. The second thing is done is that security IP actually enables the main CPU, which is then operational, and the system can start running. Now we have to understand that this power up sequence executed by security unit is done from the boot ROM code, which means that we need to preload the boot ROM with the specific data. So you may say that we can easily just get the same ROM data that IP provider used for their block level verification. So this is not actually correct. Why? Because IP provider is not aware of our power up sequence. So in their boot ROM, they have only internal configuration of the security unit, but they don't know our address space and our transfers that need to be done. So we need to produce our own boot ROM. So there are a few ways how to do it. One way is to dive into the software tool provided by IP vendor used for generating boot ROM and to implement our power up sequence. This is not quite acceptable because it could take significant time and effort. The second option is to actually provide all the necessary information to IP provider and ask them to create this boot ROM for us. This may sound reasonable, but we have to understand that this boot flow boot flow can change during the time, so the power up sequence changes, and each time we change it, we may need to request new boot ROM code from our IP provider, which could create a lot of dependency, which we want to avoid. So the best way to do it is actually to communicate at the beginning with the IP provider for them to create certain placeholder functions which will be empty for them. So when they generate boot ROM in block level, these functions will be executed, but they will be empty. And for us, they will not be empty, but we will populate it with our power up sequence. So when we use their tool for generate boot ROM, we will have our power up sequence in their boot ROM code. Now there are two modes of operations, and then it means that there are two different boot flows. One is non-secure and the other is secure mode of operations. Now you may wonder why do we need non-secure boot? So this is secure unit and we need to have only secure mode of operation, and this is partially true because in real life we want to execute only secure boot flow and we want to use secure mode of operations, but you have to know that in secure mode of operation all debug units and debug interfaces in the SoC are locked and all data is encrypted. So in case the chip is produced and during the testing we find it doesn't operate correctly, it's nearly impossible to debug it when in secure mode of operations. This is why we need to also to have non-secure mode of operation, in which security unit is enabled. It's operational, it can be accessed, but it doesn't really encrypt the data and it doesn't lock debug interfaces. So in the next two slides, I'll present non-secure and secure boot flows. So the first test, non-secure boot. So as mentioned before, we need to produce our boot ROM data and to preload boot ROM memory with it. We also need to have OTP data. This data can be easily generated using a software tool provided by IP vendor, and we need to preload the OTP memory with this data. So why do we need this data? So this data contains certain configuration information needed by security IP. One important information for this test is in what operational mode it works. So security IP will learn from OTP that it works in non-secure mode of operation. We also need to preload the memory, let's say flash memory, with the program executed by main CPU. I'll come back to this later. So how does it work? When we power on the SoC, PMU starts executing the power up sequence. Part of this sequence is to provide clock to security IP and to take it out of reset. Once it happens, security IP reads from OTP the information that it should operate in non-secure boot, and it reads data from boot ROM and executes it. So part of this is the power up sequence that I mentioned before. So it first reports back to PMU that it's up and running, and the second thing is that it enables main CPU. So this is more or less the end of power up sequence, but it's not the end of the test. So basically we need now to check that power up sequence was successful. How to do it? So when main CPU is out of reset, then it accesses flash memory, reads the simple program and executes it. So this program can be very simple. It can be just simple write and read access to some debug register in the system. It can also be more complex, like access to system RAM or some other memories, but it's not necessary. So what do we check? We check that main CPU executed these transfers correctly. So in case it didn't, we need to find out why. So this can be a bit tricky to identify because the flow could break at many steps. So it is a good idea to add checkers to other points in the system as well. Secure boot is somewhat similar to non-secure boot with some very important differences. So boot ROM we preloaded, OTP we also preloaded. Now OTP will say that system works in secure boot. Now regarding the flash memory, so it now must contain different data. So it contains the content of the IRAM and DRAM of the security IP and also IRAM and DRAM of the main CPU. But this data needs to be encrypted. So this can be relatively easily done by software tool provided by IP vendor. So now when all of this is preloaded, then we power on the system. PMU does its part of the sequence. Security IP starts booting, reports back to PMU that it is alive, and then it starts reading encrypted data from the memory. It decrypts it, it populates its IRAM and DRAM first, and then it writes decrypted data to the IRAM and DRAM of the main CPU. Then it does the part of the power-up sequence. It enables main CPU, and this is the ending of power-up sequence. Now we need to actually check the power-up sequence was correct. How to do it? Well, when main CPU is enabled, it will read its own IRAM and DRAM. It will execute the same program as in non-secure boot, and we will check it. So the same as in non-secure boot. However, there is another very important aspect of secure boot. Secure boot actually locks all the debug interfaces and blocks in the SoC. So at the end of this test, we need to try to access these interfaces and blocks and make sure to check that access is denied. Next two tests are related to service requests. So they are TRNG and crypto service. So basically these features are very well verified in block level. So we don't need to focus on their functionality, but rather we need to check that we can correctly send requests to these blocks and that we can obtain generated data from them. In case of TRNG, we need to trigger our main CPU to send instructions to the security IP, and then when this security IP takes instructions, it generates random number according to the configuration and writes it back either to the memory or to the main CPU. So we need to check that this number arrived to the location. Crypto service is actually request from CPU to encrypt data. So it's a bit more complicated than TRNG. It starts the same. Main CPU sends instructions to the security unit, but it doesn't send data. Security unit needs to obtain data itself using DMA. It accesses DDR or some other memory, takes raw data, it encrypts it, and writes it back. And we need to check that this procedure is executed correctly. So debug interface is very important feature of the security unit, because once chip is produced, and if it shows some unexpected behavior, this behavior could be related to security unit operations. So we need to be able to access a security unit and check what is wrong. So this debug interface actually operates differently depending on the mode of operation. So in case of a non-secure mode of operation, we can access it. In case of secure boot, we cannot access it no matter what we do. So what do we need to check? We use JTAG, for example, to access this debug interface from the outside. So first, in non-secure mode of operation, this debug interface is not automatically unlocked, but we need to go through specific hardware authentication procedure in order to unlock it. So we need to check three scenarios. We need to try to access it without any authentication and see it is locked. We need to perform intentionally wrong hardware authentication and see that it's still locked, and then at the end we perform correct authentication and see that we can access a complete address space of the security IP unit. So in case of secure mode of operation, we need to perform all three scenarios again and make sure that we cannot access security IP in any way. So security unit can generate alarms and interrupts. So usually digital sensors activate alarm. Digital sensors are specific blocks that can detect changes in voltage, radiation, temperature, or frequency. So in our simulation, we need to, for example, to increase the frequency and make sure that alarm is triggered and to check whether it really happened. Regarding interrupts, there are different sources of interrupts like ECC errors or OTP errors, authentication errors. So we need to check that all of these propagate to our interrupt controller. And depending on mask configuration, that interrupt controller forwards this information to the main CPU. So it's very important to check performance. So we didn't do any good if we integrate security IP, which is functionally correct, but it has severe negative effect on performance. So how to do it? We need to identify all critical paths in the system and to create tests for each of these paths. I'll just give one example in my presentation and in my paper. So for example, security IP executes some crypto service, which means it uses both of its DMAs to access DDR memory. So at the same time, Ethernet accesses the same memory, and we need to calculate expected throughput in this case and make sure to check it's indeed met. So we found several bugs during this procedure. The first set of bugs is related to PMU flow. So the example of the one bug is that PMU did not provide clock to the main CPU, and security IP executed already its part of the power up sequence and tried to enable it. So basically main PMU is never enabled and the SoC got stuck. The second bug is related to security IP timeout. So as I mentioned, the part of the power up sequence that security IP execute is to notify the PMU that it is up and running, but this default timeout was made too short. So basically the boot flow wasn't done yet. Timeout already expired, and PMU started executing fallback sequence because it thought that security IP is dead. Another bug is related to AXI connectivity. So ID port was eternally made too narrow, so the transfers were corrupted. And also a very important bug to be found is SPI debug port, which was supposed to be locked in secure boot mode, but it wasn't, so it was potential gateway for the pirates. So the conclusion is that verification of security IP integration is complex task because it it has many aspects that needs to be verified. So the method I presented is fairly compact and effective because it's based on detecting the gaps between block level and system level verification. It uses a relatively small set of tests, and it also uses standard tools and methodologies that most of us already use, and there is no need for additional tools. Please feel free to ask questions now. Thanks.